This is our second lecture on energy balances, and we are going to go into more details about energy balance procedures, and we will also cover mechanical energy balances. However, we will do few of those in this course. So now that we are going to be doing energy balances, it will be useful, in fact you should, include such information on your flow charts, such as temperature, pressure, enthalpy, velocity and elevation, which is useful for mechanical energy balances. However, we will do few of those in these courses. But you should also include the state of the liquid, whether it's solid, liquid, or vapor. Let's look at an example calculation of an energy balance. We have 10 kilograms per second flow rate. This is an m dot of saturated liquid steam at 70 degrees C. You can find the H hat in kilojoules per kilogram on the steam tables for saturated liquid steam at 70 degrees C. And that steam is pumped too. All right, so that tells us this is the entering steam. This is now leading us to what's happening to that steam. It is pumped. Okay, the inlet steam, 10 kilograms per second, 70 degrees C saturated, is pumped to a high pressure of 100 bar in an adiabatic pump where it enters a boiler. The pumping process is essentially constant temperature. In fact, only for liquids, when you have a adiabatic process, can it be approximately constant temperature. Normally, when you have an adiabatic process, it is not constant T, not, okay? But in this case, it's approximately constant temperature for a liquid. All right, and then it is heated. So we are adding Q from a fuel burning or something. We're adding heat to the steam, and it is now going to be 750 degrees C, and the process is a constant pressure process at 100 bar. So for our pump, we have no heat transfer. It's adiabatic, and we're neglecting these, which is a good approximation, okay? But we do have a delta H, and we have a shaft work. So delta H is equal to the shaft work. On the other hand, for the boiler, there's no shaft, so we have delta H is equal to Q, no shaft work. And you can use the steam tables to find the specific enthalpies for each state. Okay, so here I have found them, but I urge you to look on the steam tables and find these values of steam. And if you cannot find them, then you should come to office hours and get help, or ask in class. All right, so we have the values at these three different states. Okay, this one here is an unusual state. This is subcooled liquid. And the subcooled liquid is on the superheated tables, even though it's not superheated. The subcooled liquid steam information is on the superheated steam tables, and if you look on there, it's under this staircase, okay? And all the data in that staircase is subcooled liquid. Okay. So we find the data for the H values, and then we can do an overall energy balance, which would be the final minus the initial, and we can also calculate the individual heat of the boiler and the shaft work of the pump. And you can try these out for yourself. Find out that the heat of the boiler is 36,870 kilowatts, and the shaft work is 90 kilowatts. So the first video quiz you have is A 12 megawatt turbine is used to power a mill. Inlet steam is delivered to the turbine at 20 bar, okay, at a flow rate of 50 kilograms per second. This is superheated, okay? So we do not have enough information to get the H, okay? We do not know, just based on being superheated at 20 bar, that we don't have enough information to know the H. The flow rate is given. The steam exits the turbine at 10 bar in saturated vapor. Here we do have enough information to get the H. So you can look that up. Now, so with that, first you're going to calculate the outlet enthalpy of the turbine. To calculate the inlet enthalpy of the turbine, you need to use the energy balance. Okay? Delta H is equal to Q minus W. Okay? What are we going to do here? Q is 0 for a turbine. So delta H is equal to minus W. And I gave you the W. Okay? So use that information. A turbine, the system does work, so the work is positive. Okay? And you're going to plug it into this minus W here and find the inlet H from this equation. Okay, and then once you find the inlet H, then you can find the temperature of the inlet steam.